Okay, last time we wrote down some rules of definite intervals. We're going to do that one more time to refresh the memory on what you're allowed to do, what's legal. And definite interval is different than an indefinite interval. So definite interval means we have a lower bound and an upper bound that we're taking the antiderivative on. Rules of definite intervals. Okay. First of all, remember the lower bound actually from A to B, so A to B. What if your bounds are in reverse order? They should be in order from left to right and then right. So remember what happens when you rearrange them? A negative comes out. So it should be from A to B of f of x dx. But by rearranging them, a negative comes from the interval sign. Okay? That's sigma. Okay, what's the rules with the constant? If we have a constant multiplier, so from A to B, we have some constant, we'll call it K, and that's x dx. So that constant K really needs to be integrated with an integral. So what do we do with it? Just like derivatives, it just pops up, right? To derive or integrate the rest of it, and then at the end, the constant multiplies at the end. So any constant multipliers can be popped out in front of the interval. It's still times and everything, but it can be popped out in front. Okay? Sum and difference. This means you can break up interval as long as it's like in polynomial form. Like say we have f of x plus or minus g of x. And all of this with respect to dx, remember dx is the width of your rectangles underneath the curve. And we're putting infinitely many rectangles. Okay, so the dx is your width, and f of x plus g of x will be the length or the height of the rectangles. You can separate these into two separate integrations. So maybe it's easier to integrate f of x separately from A to B, and then integrate g of x separately. This also works for difference, so we're going to put plus or minus. And the last main one is additivity. If we have the interval f of x, we're integrating f of x dx from A to B, plus we're integrating the same function f of x again from B to C. So the first interval stops on B, and the second interval starts on B. This is not the same thing as integrating from A all the way over to C. And all the way from A to C. Okay, so those are pretty much the basic one you need to remember. Okay, last time, I know, so we wrote down 3 ways to integrate. What's the first one I talked about? Estimation. Using LRAM, right RAM, MRAM. Estimation. Using the RAMs. Those are called Riemann sums. A guy named Riemann, back in the day, created that method of estimating using rectangles underneath the curve. In our last section, we started finding exact areas underneath the curve by using what? geometry. And today we're actually going to start doing the antiderivative. Derivative. No, anyway, derivative. That's better. Okay, so, now let's think about it. If x squared is the derivative, what's the original function? 1/3 x cubed is a possibility. What about 1/3 x cubed plus 2? Does that have the same derivative? Well, 1/3 x cubed plus 800. Is that the derivative still x squared? Or 1/3 x cubed plus infinity? So, can we say plus the constant? Let's see. Actually, on the response questions, if you're asked to do an antiderivative, oftentimes they give a point just for remembering to put plus c. So if you forget to put plus c, you're losing the whole point. There's only 9 points, remember, on each of the problems. So what's the antiderivative of 4x cubed? Okay, x to the 4 plus c, we agree with that. Typically reverse it, we divide it, we bring the 4 down, and then decrease the exponent. So that's perfect, Alex. But there's always a plus c, because you can take the derivative of a constant and get 0, right? Any constant. Even if it's pi, your derivative of pi is still 0. What about this one? So we've got 3/4 x to the 4/3 plus c. Let's make sure that works. If we bring down the derivative and decrease the exponent by 1, what's a fancy way to write 1? That is helpful for this fraction. 5/3. Okay, and then derivative c becomes 0. We actually get 1/4, and 4/3 minus 3/3, would that be 1/3? So 1/4 x to the 1/3. We're close. Oh, whoops. Wait, now I'm confused with them. Oh, I put that in third page too. I translated the super bowl and go backwards. Can't let things sound with you. Okay, so again, remember in London. Oh, heck. Okay, alright, 3 points is supposed to be here, yes? And I bring down, there we go, and then it all cancels out. Yeah. Okay, so I want you to talk together, and you write a mathematical formula for how we basically were undoing the power rule, right? So you can come up with a mathematical formula for undoing this power rule. I wrote 2 by 2, so I'm going to put it right here. Let's start off with notation. So the derivative always comes here. We're integrating it. So if a derivative of x to the n, what would a formula, a mathematical formula be for any generic antiderivative undoing the power rule? You're close. You're really close. Just need one more detail. Okay, think of an x squared. In my derivative, the power is a 2. over in my antiderivative, what's the denominator? My antiderivative for the first one. Yeah. That would work. Also, I need to put that's the same. Of course.
Hey, good. What are you talking about?
We used to have the interval in front of it, interval SBN dx. Okay. So again, here's the derivative, that's squared. But what becomes the denominator? What is it? A 3 in the denominator. X cubed. What becomes the denominator that cancels out? 4. It was 4 over 4. This one's 1/3. And our denominator, what kind of different comes a fraction? But things can be what's going to confuse you. So these two are really close. What's going on with the denominator each time? You add 1, and it becomes the denominator. So we're going to do 1 over n plus 1. X to the n plus 1. So then the power increases and you divide by that power. Yes. Yes. Okay. So the and we'll put it here. Let's put our bound A to B as well. Okay. So we're going to talk about the fundamental and calculus next. And there's 2 parts to it. We're not doing part 1, we're doing part 2. This is how you derive 1 to the antiderivative. If lowercase f is continuous. So you know your requires continuity, right? We don't know what terms. We have MDT, IDT, UBT, extreme body term, intermediate body term. The specific words we need to make sure are checked off. So this one requires that we're continuous at every point on the closed interval, A, comma, B. And if capital F, so there's a difference between a lowercase f and a capital F. If capital F is any antiderivative of lowercase f on the closed interval A. This is a word E, but it makes sense, promise. Everyone is A to B, then this is how you derive. Notice in my interval, do I have a capital F or do I have a lowercase f? So the derivative is lowercase. We don't color code those. The derivative is our lowercase f. When you take B, as long as f is continuous in the closed interval, when you take an antiderivative, we get capital F. Capital F is any antiderivative on that same closed interval from A to B. Today we're actually going to learn how to evaluate it by hand. So the fundamental theorem tells us we can then plug in our upper bound into capital F, subtract our lower bound into capital F, and that will tell us the exact area under the curve. Okay? Let's go over to the first problem. Oh yeah, the last was booklet. That's so weird that they did it that way. Sorry. Okay. Using geometry first, we're going to evaluate this. And so it's the same one with antiderivatives. What does this line, I gave away, what does this graph look like? A line with a, where's the y-intercept? 1, that's the slope. 2, so using geometry, we have there's a pure 1, And it's that value from 3, so we go up 2 over 1, up 2 over 1, up 2 over 1. So from 0 to 3, what shape is that? It's a triangle. It's a little itty parallel side right here. It's picture. So again, I'm going to open your eyes, please. Again, we're going to do 1/2 of base 1 plus base 2 times the height. I should probably actually focus on it and do that. And put it above. And then put the numbers in. So Chris, can you tell me base 1's value? The base is actually parallel, so let's place them sideways. 1, what's the other one? That's because we plug in 3, 2 times 3 plus 1 is 7. What's the height? Which in this case is tilted sideways. From 0 to 3 is 3. So parentheses first, we get 8. Now times 1/2 times 8 is 4 times 3, so we have, I really should just go down, 12 units squared. That's my geometry. We're just showing you the exact same thing as we do antiderivative. Antiderivative power rule. So we increase the exponent by 1 and then divide by that new exponent. So this is x to the first power. What's the increased power? X squared. A 2 is still there though, and then we divide everything by that new power. We increase the exponent and then divide by the new power. So the new power is 2. This 1 is technically x to the 0 power. That's why it's not written. So we increase the exponent. It goes from 0 to x to the first power. So the 1 is still there, x to the first power. We divide by 1. Now, we also have to do plus c if it's an indefinite interval. So we have defined upper and lower bounds. We don't need to put plus c. It's from 0 to 3. So we just do like a bracket. 0 is the lower bound, 3 is the upper bound. Okay? And we have to plug them into the right order. Actually, let's simplify first. X squared plus x. That'll make it easier to put in. From 0 to 3. We're in the line. Or a bracket. Doesn't really matter. Right? So first plug in that upper bound. So lowercase f is 2x plus 1. What's uppercase f? Capital F. X squared plus x. We've got plus c, we didn't have actual bounds. So we have bounds, so we're going to plug in the upper is 3 squared plus 3. Subtract the lower bound. The lower bound has the brackets around it, so we have to subtract everything is 1 squared plus 1. Does that make sense? Okay, 3 squared by 9 plus 3 is 12. Minus 1 squared is 1 plus 1 is 2. So, what? Oh, it's a 0. I mean, that's not how that goes at the end of the day. Okay. 0 squared. Because what should we be getting at the end? Should we get the same answer as before? Oh, yeah. Units squared. So there we go. It's the same. I lower bound is 0 on that one. Okay. Now looking at trade function. Okay, careful. The derivative is sine. What's the antiderivative? If you take the derivative of this function, how do you get positive sine? Good job. It has to be negative cosine, because when you take the derivative, when you d dx negative cosine, become positive sign. Okay, so we get our capital F, our antiderivative, is negative cosine x, evaluated from what goes on top. And what goes on bottom. 0. So same order they're written here, as long as they are in the right order, which usually are. So now we do over here, nice arrows, the gradient can follow your thought process. Negative cosine of which one did I plug in first? All you need to open your eyes and your shadow. Okay, which one did I plug in first? Don't put that first. Subtract, don't put brackets. So I just put that subtract cosine 0, is that right? Is this right? Subtract cosine 0? You can really drink that as your lips. Negative, subtract negative cosine 0. Okay, what's the cosine function? I just counted some quick little graph. It's actually negative cosine function. So doesn't that graph look like this for negative cosine function? Here's pi, here's 2 pi. So negative cosine of pi is what value? 1. Subtract. Negative cosine of 0 is what value? Negative 1. So our area is, I should put this is 2 actually, not 0. Okay, we have subtract a negative, units squared. Okay, would you do number 3 really quickly? It's very similar to the vowels. What's wrong with the hiccups? You just never get through it so long. Okay, quickly, number 3. You just go so far. Okay, how is number 3 different than number 2? The vowel. What's the only thing different? What's the antiderivative sign? Negative is the same as the last problem. Make sure you always put the x. But it's from 2 pi to 0. So I'm going to put equals negative cosine of which one do you plug in first? 2 pi. Subtract. Make sure you bracket the second part. Subtract a what, Chris? Good. So negative cosine of 2 pi is negative 1. Subtract. What's negative cosine of 0? So the area of the curve is, and why do we get a 0 area when it's actually a graph? It's because of the sign area, right? These two bottom sections cancel out in the upper section. Okay? Flip it over, yeah. Because it's only, you have 0 to pi, but it's supposed to be 2. Oh, because it's, it's actually associated that with, because it's actually the sign graph. The area underneath the curve. So, yeah, the sign graph from 0 to pi is 2. That's one you have to memorize, right? Okay. And then from 2 pi, those two cancel each other out. That's better. Okay. All right, number 4. Yeah, we haven't been on these yet. Think about it. It's terrible. Terrible copying. 1 over x minus 1 over x squared dx. Okay. Well, you can do this in 2 ways. We can do power rule, which we've already practiced, or we can use another rule. If we use power rule, I would rewrite this. Isn't 1 over x the same as x to the negative first power? Minus 1 over x squared is the same as x to the what power? Negative 2 dx. So we use power rule. Means we increase the exponent and divide by the new exponent. So if our exponent's negative 1, we increase it, we get x to the x to the 0. We divide by 0. Okay? Which is a little bit of a problem. Over here, we increase the exponent. We negative 1, we divide by negative 1. From 1 to 3 was a 4. It's a 3. 1 to 3. Okay. Okay. This is an issue, right? We can't divide by 0. So let's think of a different rule. What has the derivative of 1 over x? Natural log. Okay, so this actually becomes, that's why we can't do power rule because x can't be 0, right? So we have natural log of x. That's why we can do fine with power rule. Power rule works just fine. And subtracting a negative actually makes that a positive x to the negative first power. So I'm just going to write as 1 over x. And when I plug in, it makes life a little easier. Okay. I wish I go sideways. It's much better to go vertical. So first we plug in 3. Natural log of 3 plus 1/3. Make sure the first one doesn't really matter if it's bracketed, but the second group has to be bracketed because we're subtracting everything. Natural log of 1 plus 1 over 1. Got arrow here happens, so the greater the color work. The natural log of 3 and natural log of 1, are they going to be like terms? Huh? They're log-based trees, but their parts are different, so they're not like terms, right? So we have natural log of 3, this is actually a minus natural log of 1. But is the 1/3 and this guy going to be like terms? 1/3 and negative 1 are like terms, which is the same thing as negative 3 over 3. So 1/3, that's going to be negative because we'll subtract. Minus 2 over 3 is minus 2/3. Okay, yeah. Because the derivative of natural log x is 1 over x. If you use the power rule, you get division by 0, which is an issue. So the derivative of natural log x is 1 over x, so the antiderivative is natural log x. Okay, we'll do the activity, so let's try, we'll just do number 6. So we'll move on to the next part. Integrating e to the x plus x to the 2/3 dx from 1 to 3. Okay, so all I have to do is power rule thing. This is derivative inside the parentheses here. What has the derivative of e to the x? E to the x, we take the derivative of e to the x of itself, right? So we get e to the x. Now this one's a power rule. We keep the exponent. Increase it by 1. So 2/3 plus 3/3. And then we divide by the new exponent. The new exponent ends up being 5/3. So I'm going to rewrite that because we have bounds here from 3 to 1. E to the x plus x to the 5/3. I also move my 5/3 in the denominator in front as a 3/5 for the multiply. From 3 to 1. Which one do we plug in first? 3, just like you did the book. Your higher bound, subtract your lower bound. E to the third power plus 3/5 x. Oops, not x, I'm going to 3. E to the third power plus 3/5 times 3 to the 5/3 minus, I have to go to the next group. E to the first power plus 3/5 times 1 to the 5/3. Okay. So, if we look at Mayor and Sally, what do we do first? The group B, which will be here. Anything in group B to do? Inside of group B? I don't think so. I think that the first thing we need to do is exponents. What's 3 to the 5/3? Do you know how to break that apart? 3 to the 5/3 is actually a radical. What's the index? 3 to the 3 to the 5th power. Or 3 times 3 times 3 times 3 times 3. So we're looking for a grouping of what? 3. So we can pull out, we get 3. Actually, the other one has a 5/5. The base has to be the same. We get 9 to 9/5. Let's see. So we have cube root of 3 squared, which isn't going to help. It's kind of messy. Let's see. Yeah, okay. So this becomes times 3 to the, what do we do over there? Times 3 to the, times 3 to the 2/3. Minus e to the first power is e, plus 3/5, 1 to the 5/3. That's cube root of 1 times 1 times 1 times 1 times 1. Does that change at all? 1 to the 5/3 is just 1. Okay? We distribute that in and there's negative e minus 3/5. Do you have any right terms with the first part? Are there any right terms? Yeah, but that's one for the base is the same. And with the same basis. When we, but we're not multiplying. We are adding. So actually, I'm going to same exponent as well. So we actually can't combine those. E cubed minus e to the first power. This becomes 9/5. Oh, we both have a negative 3 to the 5th. Plus, so we have 9/5 times 3 to the 2/3 minus 3/5. Would that be mathematically equivalent to this? Would that be mathematically equivalent? They both have the 3/5. Okay. And then moving on to calculator section, could you stop there and leave it as everything that looks? as long as it's mathematically equivalent. If it's a calculator section, and it asks for an approximate value, you can just plug it all in and approximate 4 decimal places. Okay, let's go to the activity really quick on the back side. Average value. Average value of a function. Is when you're finding the average value. No. So, if you're integrating f of x dx from a to b, to find the average value, you integrate, and then you divide by the upper bound minus the lower bound. Usually we write it like this, though. 1 over b minus a, integrating f of x from a to b. Okay, we're going to do a quick little activity. Everyone needs one of these. You find out what that means. What if you're averaging all of your number of siblings you have? How do we find the average of the number of siblings you'll have? Exactly. Add them up, divide by the number that you'll have. So, we are trying to find essentially the average height. So, in the next case, it has the instructions of what we're going to do. I'm going to sanitize it really quick. Okay, so I gave you a graph paper. What you're going to do is as first, like I say, use your M&Ms, fill the area between the curve from 0 to 3. Compensate as best you can, but M&Ms will stick out above the area, and once you don't quite reach it. And to calculate the area, our unit squared is 1 M&M squared. From 0 to 3. On the bottom, it's labeled 0.51, 1.52, 2.5, okay? From 0 to 3, how many unit M&Ms does it need? Do you need to cover underneath the curve? And I don't really know what this is, so you might have to combine M&Ms. Okay. Hurry. How many unit M&Ms to fill that whole section from 0 to 3? That's a 3, yeah, we know that. And then how many again? approximately. Compensating for ones that came over outside of the area you're supposed to be calculating and those that empty space. Approximately how many are we getting? 61? 16? That's about where we're at. Approximately 60 or 61. Okay. Taking the same number of elements that are currently on your paper to the next step. It says rearrange them into a rectangle. Now rearrange it into a rectangle of the base along from 0 to 3. It's a perfect rectangle. So move the top ones down until you get a perfect rectangle with the base of your rectangle from 0 to 3. Not adding anymore once you have your another curve using the same quantity of M&Ms. So take these top ones, move them down. It can be outside the curve. The rectangle can go past the curve. And I didn't know how tall the rectangle is approximately. Approximately 6 tall, or 6 M&Ms tall, but on the y-axis it's at 3.5. 4. Okay, so when you fill in, you get something like this, right? So when I say average value, what you're finding is, because remember on our survey, we have a bunch of rectangles, interlinear rectangles, small ones, they get taller and taller and taller. So you're finding the average height. The average height is right here. Okay, which yours looks like it's roughly between 2.5 and 4. So when we use this formula to find the average value of 1 over b minus a from 0 to b of x to x, the x that we're finding is the average height of each rectangle. Not each, of the rectangle, the infinitely number of rectangles. Okay, we are going to do a couple average value problems next time because we're out of time. You can eat those M&Ms. On your homework, your purple slip, that's what I'm writing in a couple minutes. You can now do the next 3. You don't know how to do average value quite yet. You have the formula, you can try some. But we have, because we're doing 3 and 3, 4 for 2 days combined together, so it's kind of a more for 6, 3, and 6, 4. So you can do 6.3, 135. You can do 6.3 that says integration using antiderivatives, and 6.4 that says integration with the antiderivatives. So you can do those first 3 lines. Next time we'll keep working on 3, 4 and 3, 3 and learn the other stuff. Yep. Okay, clear? And do Thursday is your whatsy, right? What the whatsy? Does everyone have whatsy number 5? That's the yellow one and that. Put it all to the right if you don't have your whatsy. Yeah. Because the minus and negative makes it a positive, right? And this is actually a negative one. Did you very well? So in the beginning, I changed this into minus x to the negative 2. So we increase the exponent, which if you increase the negative 2, it becomes negative 1. And divide by the new exponent, negative 1. Yeah, 1 over b. Yeah. It's possible because this is the negative cosine graph. Positive cosine graphs are up here. All right. Thursday after school, we still have our AP review. Please come and join. We'll answer questions on the example areas next time. Good stuff.